Hi everyone, my name is Alex Perkins, and today I'm going over the Bi-illuminant dichromatic reflection model. I'll start with a quick recap of the standard dichromatic reflection model and why its assumptions matter, look at why that model breaks down, and then walk through how that issue is fixed, and last cover why it matters. Standard dichromatic model. So as a quick refresher, the standard dichromatic reflection model describes the color we see on certain materials, things like plastic, paint, ceramic, and paper. These are materials where light doesn't just bounce off the surface, some of it also gets absorbed and re-emitted by tiny colored particles underneath the surface. The model says the color we see is made up of two parts added together. Surface reflection, which is light bouncing directly off the top, and body reflection, which is light that went slightly under the surface and picked up the material's actual color. Here's an important detail. This model assumes there's only one light source lighting the scene, and no other light bouncing around in the background. That single assumption is exactly what's going to fail once we step outside. And everything I cover for the rest of this presentation is just what happens when that assumption isn't true anymore. Why it breaks down outdoors. So here's a concrete example of this problem from Professor Maxwell's own PhD thesis on image segmentation, which is about figuring out which pixels in an image belong to the same object. His work points out that a lot of early methods for doing this only worked if the whole scene was lit by one single, evenly colored light. Klinker's method, which, for example, looked for a specific pattern in the colors of an object to figure out where a highlight was, but that pattern only holds up if the whole object is lit by the same single light. Bakchi's method needed an actual white card placed in a scene, just so the algorithm had something to compare against to cancel out the lighting. Healy's method for telling metal apart from plastic only worked with one white light and broke without it. As Professor Maxwell puts it directly, none of these older methods could handle a scene lit by more than one color of light at the same time. This matters because it shows this wasn't a small detail researchers forgot about. It was a real limitation that caused these systems to fail as soon as they left a simple single light setup. Two light sources modeled explicitly. Here's where the problem Bi-illuminant dichromatic reflection model solves. Instead of assuming there's just one light source, it says there are two lights hitting everything outdoors at once. The direct sunlight and the ambient light from the sky itself. A spot that's in direct sunlight gets hit by both of these at the same time. A spot that's in shadow is blocked from the direct sunlight, since something is standing in the way, but it's still getting lit by the sky, because skylight comes from the entire sky above, not from just one single direction you could block. So a shadow isn't just a darker version of the same color, like you might expect. Since the only light still reaching that spot is coming from the sky, which is blue, the shadow shifts toward a slightly blue color too, not just a dimmer one. The older single light model has no way to explain that at all, since it only ever has one light color to work with. So here's my example. A sidewalk on a sunny day. Here I have a cast shadow on a sidewalk on a sunny day and built an RG chromaticity histogram which plots pixel colors with the overall brightness removed. This should help show color differences even between a bright spot and a dark spot. What was found is that the sunlit part of the sidewalk and the shadow part landed in almost the exact same spot on the histogram, forming one tight cluster instead of two separate ones. At the time, I read that as meaning the color of the sidewalk didn't really change between sun and shadow, only the brightness did. Looking back at that now with the Bi-illuminant model in mind, that's a simple scenario, where the sky color and the sunlight color happen to be close enough, or the sidewalk itself is plain enough that the shift is hard to notice by looking at a basic histogram. But the Bi-illuminant model tells us there should be a small shift toward blue happening in that shadow, even if it's too subtle for this photo to clearly show it. So why this matters? Why does any of this matter in computer vision? A few reasons. First, shadow detection and removal. If you know shadows shift in color, not just brightness, you can build a program that recognizes shadow edges as shadows, instead of mistaking them for the edge of an actual object, which is a common mistake in outdoor image processing. Second, color constancy, which is just a general problem of figuring out an object's true color no matter what lighting it's under. Outdoor scenes are exactly where that problem gets hardest, since there really are two different colored lights involved. So a model that counts for both gives a much better starting point. Third, this matters for anything that uses color to recognize or track objects, or even something like an image search project I built earlier this term, since assuming there's only one light source could cause a program to misjudge the color of anything that's partly in shadow. So to sum up, outdoor scenes are lit by two different colored lights at once, and shadows are better thought of as areas mostly lit by that blue skylight, not just darker copies of the same surface color. That distinction matters for shadow detection, color constancy, and any color-based vision task working with real outdoor images. That sums up my presentation on the Bi-illuminant dichromatic reflection model. Thank you for watching.